Good morning. And thank you, Congreso Futuro, for inviting me to talk about the incredible things that are happening here in Chile and in astronomy. I hope by the time I have finished, I will have convinced you that telescopes are powerful machines that change the way we think, and that Chile is playing a central role in this revolution. Think about it. For thousands of years, our experience of the universe has been solely what we could see, what we could touch, what we could hear. For millennia, we sat as communities and looked up at the dark sky, like these in Chile, and asked fundamental questions like, where have we come from? Where are we going? Are we alone? Guided only by our experience and our intuition. So was it surprising that the world was flat? It was only when we started making measurements did we realize, oh, from a new perspective from in space, our intuition was actually impeding the way we could comprehend the universe. Most revolutionary of all was this man here, Galileo. He took a small telescope and for the first time pointed at the sky. Here he is showing the Dodge of Venice, what his telescope could do. He realized that the sun, not the Earth, had to be the center of our solar system, but more importantly, that the Earth was traveling around the sun at an incredible speed of 30 kilometers a second, a speed that we can't experience, we can't feel, but that was the universe revealed through observation using a telescope. Of course, for those heretical ideas, he spent the last 10 years of his life sequestered in this room. But he was able to write down what he saw. People read what he wrote. And in fact, they built their own telescopes and repeated what he did. And so the scientific revolution commenced. Edwin Hubble himself used the telescope to discover that the universe was expanding. But as importantly, he gave us a new scale to measure space and time. He realized we have to use millions of light years to measure distances. That's the distance a light ray gets to travel in 1 million years. An incredibly unimaginable distance. And the Hubble Space Telescope, named after Hubble, was launched in 1990, the largest space telescope we'd ever launched at the time, above the atmosphere, that gave us a completely new and clear view of the cosmos. Something we had never seen. It takes actual pictures, and just as Ansel Adams had taken photographs of the US West to reveal a landscape to those who couldn't travel there, here in space, the Hubble can also take its own landscapes. These are actual pictures taken with the Hubble Space Telescope. Of course, we have to use a different scale to measure what we're seeing. We have to use light years. It takes light 5 years to travel from the bottom of this picture to the top. And of course, we know the universe is expanding, and that stretching of space and time means the more distant objects become redder and redder and move into the infrared. So to see the most distant objects in our universe, near the edge of time itself, we had to build a new telescope for space, the James Webb Space Telescope, that could only see the universe at infrared light. And to see that, we had to take pictures at infrared wavelengths and then transpose them to the optical so you and I and all of us can see what an infrared universe might look like. And in these next pictures, you'll see a galaxy taken with the Hubble. This is a galaxy with just an optical light, then the combined light with James Webb, and then this final picture of the same galaxy taken in only infrared light. you can see the spiral structures that built this galaxy revealed uniquely with the James Webb Space Telescope. So in 2022, when we pointed this telescope at a blank piece of the sky, no bigger than a grain of sand held at arm's length. Just think how small a spot in the sky this is. A grain of sand. And we stared deeper and deeper, just holding the telescope steady, looking at this part of the universe. This is what we saw. Thousands of galaxies on a point of the sky no bigger than a grain of sand. And if you multiply those galaxies across the entire sky, take all those little points and do the math, you discover that there are 2 trillion galaxies in our observable universe. 2 trillion. Now, the James Webb doesn't just take pictures in 2 dimensions. We can measure distances. And so we can go out and measure distances and actually create a 3-dimensional view of the galaxies in our universe stretching back in time. And we can make a movie, and we can fly through it. So let's go. Here, we're flying through actual data. This is not a simulation. These are galaxies seen by the James Webb. We are traveling at a phenomenal speed here. 400 million light years a second, deeper and further back as we go. And as we fly deeper, the galaxies become less copious, they become red. And this little red dot that begins to appear here, its light started its journey 13.4 billion years ago. You're looking back in time, 13.4 billion years. Now, we don't just study the universe from space. Here in Chile, we are making some amazing new observations. Using the NSF's telescope on Cerro Tololo, we had a camera put on there in 2012 and started to scan the sky, looking for all of these galaxies to try and measure the properties of the universe. In partnership with its sister telescope in Arizona on Kitt Peak, together these 2 telescopes made this amazing 3-dimensional picture of the nearest 30 million galaxies. But of course, we realized that this universe is a strange place. It's full of dark matter and dark energy, which we have no idea what it is. And to our horror, we discover we understand only 4% of our universe, which is why we built the Vera Rubin Observatory on Cerro Pachon here in Chile, to study dark matter and dark energy, try and get some insight to that 96% of the universe we don't understand. And essentially, Rubin is a 8-meter wide-angle lens that we scan across the sky every night. It has the world's largest camera of 3.2 gigapixels. And here is the data that we can take on the first few nights. The data set is so large, I'm afraid, I would need 400 4K TVs to show you a single exposure. So we're just going to have to scan through this data and look at its beauty. This data is made available to everybody in Chile and in the United States and our partner countries to study the universe in incredible detail. So every night, every 3 nights, we cover the entire southern sky, and then we start again. Importantly, we're not just taking data statically. We're taking data every 30 seconds, which means we're actually creating movies, and we see things moving against the backdrop of the stars and the galaxies, and we saw these objects on the first 7 nights of observing. Look, in every single part of the frame, there's something else moving. What are these moving objects? It turns out these are new asteroids. Asteroids that Rubin found. In the first 2 nights, we almost found 1,000. And as we kept working, we found more and more and more. And across 7 nights, we found almost 2,000 new asteroids. So, as we're hunting for dark energy and dark matter, it turns out the Vera Rubin telescope is also trying to protect the Earth, to look for that rogue asteroid that might get just a little bit too close to us. So while we're thinking about that 96% we don't understand, what about the remaining 4%? Turns out that 4% is pretty important. It contains all the stars in the visible universe. In fact, we now know there are 10 to the 23 stars in our universe. That's 1 with 23 zeros. With that many stars, in these stars are where all the elements that we're made from. And we also know in the last 20 years that around many of these stars, in fact, are planets. We call them exoplanets. This is the actual data that you see behind you of the discovery of exoplanets across the last 10 years. And we're discovering more and more every day using spacecraft and telescopes from the ground. We have now found 5,000 just looking in our own galaxy. And we know that in at least one of those planets, life is teeming and diverse. And life is complicated. It took 4 billion years to get to the point where we could ask the question, I wonder if nature has repeated this complex experiment elsewhere in the cosmos. Has it happened before? Now, if I ask many of you in the audience, how many of you think, yes, life is out there? Put up your hands and tell me. There are 10 to the 23 stars, all right? Who's brave enough to say, maybe we're alone? We are so unique. Anybody? Well done. The fact is, neither of you are right or wrong, because we don't know. It turns out that scientifically, we can't calculate whether life is out there. Life is complex, and there are lots of stars, but life is also very complex, and it could have taken 10 to the 23 coincidences for complex life like ourselves to emerge. Scientifically, we don't actually know whether life is out there. The only way we're going to find out is to observe it with a telescope. And so the hunt is on. Here in Chile, on a telescope, in fact, next to Vera Rubin telescope on Cerro Pachón, the Gemini telescope is developing technologies to hunt for planets around other stars. And in Chile, we're building some of the world's largest telescopes. See if this works. All right, take it back. The Giant Magellan Telescope and the ESO Extremely Large Telescope. Now, these telescopes, let me see if I can get it back. All right. These telescopes will look for planets nearby. If we want to go further, to look for planets around stars like our sun, we're going to take these technologies developed in Chile and move them to space. And NASA is planning a new mission called the Habitable Worlds Observatory that may, for the first time, be able to take a movie of another solar system. But is a little blue dot enough? Wouldn't we like to see if this blue dot has oceans, has continents, have cities? To make that observation, we're going to have to return to Chile, and we're going to have to invest in a new revolution. Can we see this? To do this, we're going to have to understand how to harness the quantum revolution. Can we entangle the telescopes we have here to make a single system? Can we develop those technologies? Because if we can develop these new quantum technologies here in Chile, we could imagine doing this. Taking the big telescopes we have, building 20 or 30 of them and stretch them out on a plain in northern Chile here, some 200 kilometers across, entangling those telescopes with a quantum network, feeding that quantum data into quantum memory, and taking that quantum memory and that data stored over weeks here in Chile And maybe we can build an image of a rotating planet around another star. Imagine the moment that we actually are able to make this image. Look at it slowly building up. We have to take quantum networks, quantum components, and quantum computing and bring that together in a new form of astronomy. So this was the image of the 20th century. Moonrise, Earthrise over the moon, taken by the Apollo 8 astronauts in 1968. It told us how precious our Earth was, how lonely we are. Could this be the image of the 21st century? The image of another blue planet around another star, some tens of light years from here. And as we observe this planet, and it turns to the dark side, what happens if we see cities? What happens if we only see fires? What happens if we see nothing? Imagine what we would learn. So across less than 500 years, this is how far we have come. We've started with Galileo's little sketches with the first telescope observation in the 1600s. Maybe by the 2030s we can take an image of another solar system around another star, and then maybe later on, combining these new technologies and quantum mechanics here in Chile, we can create an image of a rotating blue Earth. And what the Copernican and Darwin revolution have taught us is that such observations made here in Chile would irreversibly change the way we think and how we understand our place in the universe. Thank you.